Hello everyone, welcome to the course on large language model. This is an introductory chapter for this course. So in this specific lecture, we are basically trying to understand why large language model is important to learn. I'm pretty sure I don't need to convince you why this is an important topic, at least in today's era. We are all aware of ChatGPT and how ChatGPT has disrupted our society. So in this lecture, we will essentially try to cover the content that we are going to cover in the entire course and some of the logistics that are needed to essentially understand different content and so on and so forth. Okay, so let's get started. First things first. So my name is Tanmay Chakraborty. I am one of the instructors for this course. I'm an associate prof at IIT Delhi. Along with me, Professor Somen Chakraborty from IIT Bombay. He will also teach a part of this course. And this course also has two wonderful TAs, very supportive TAs. One is my student Anvay Chatterjee from IIT Delhi. Another is Paulomi Ghosh. She is a PhD student at IIT Bombay. So this is the course content. So this is essentially an introductory graduate level course. Okay, and the hope is that at least the audience should have some understandings of NLP. Although we will cover basics of NLP, but it's not possible to cover the details of NLP in this course. And of course, deep learning is needed. So if you haven't learned NLP and deep learning, it's recommended that you can go through some of the online courses, or you can go through some of the books. There are many wonderful books in NLP and deep learning. So these two topics are very important to learn as a prerequisite for this course. Okay, and this is more or less the content that we are going to cover. We will start with basics. Okay, so today's lecture is the introductory lecture. Then we have a lecture on the introduction of NLP. Introduction to NLP. This is essentially, it's going to be an hour-long lecture on NLP, but it's not possible to cover all different topics of NLP in 1 hour. But what I will try to basically give you a very high-level overview of different interesting contexts in NLP, and then I will also briefly cover neural networks, specifically activation functions, backpropagation, right? Different types of architectures, basic architectures in neural network, and then we will have one lecture on language model, statistical language model. Okay, where we will cover n-gram language model, different types of smoothing techniques, right? Evaluation of language model, perplexity, extrinsic evaluation, intrinsic evaluation, and so on. And then we move to word embeddings, right? So we will essentially connect the concept of distributional semantics and recent word embeddings, right? We will essentially see why old school techniques like TF-IDF based methods for word representation may not be a good idea, why we need the concept of distributional semantics, and why why we should learn word embeddings from documents, right? There we will cover word to wake and glove, these two methods. And then we move to neural language model, where we will essentially teach CNN, RNN, LSTM, GRU models for language models. And then we will move to sequence to sequence models, right, for machine translation, for text to text kind of problems. And then we will introduce attention. Okay, so these are the basics that we will cover, and then we move to architecture. In this bucket, we will start with the introduction to transformer, the transformer model, which is the foundation of existing large language models available, publicly available, or some of the black box models, right? And then we also talk about the concept of positional encoding. We will see that in transformer, the beauty about transformer is that unlike RNN, right, where RNN kind of models where sequence is important, right, and RNN, LSTM kind of models, they process a sequence of data, and that's the bottleneck, because of the sequential nature of the data, the model is not able to basically access the input in parallel, right? So transformer was introduced where they showed that how to access the input in parallel, right? And to access the input in parallel, as you understand, we essentially miss out the information of position, right? So positional encoding is essentially a way to encode the position information along with the actual information present within the token, right? Then we'll talk about different tokenization strategies, byte pair, sentence piece, word piece, and so on. Then we move to different pre-training strategies, decoder-only models, prefix model, encoder-only model, encoder-decoder model, and so on and so forth. So there we'll talk about right. So there we'll talk about BERT and different GPT models, and also T5. Okay, and then we move to different aspects of learnability, right? So these are more advanced concepts. So we'll talk about instruction fine-tuning, right? We'll talk about in-context learning. We'll also talk about advanced prompting techniques, chain of thoughts, graph of thoughts, tree of thoughts, prompt chaining, and so on. Then we will discuss a very important concept of human alignment, right? There we'll talk about RLHF, if time permits, we'll also talk about DPO and so on. And then we will see how we can essentially reduce the size of these models, right, systematically. One way of reducing the size is basically something called PEFT, parameter efficient fine tuning, where we will essentially leverage the ideas of distillation, knowledge distillation, where you have a teacher model, a large teacher model, and a small student model, and you essentially distill knowledge from a teacher model to a small student model, right, so that the student model performs as similar as the teacher model. We'll also talk about different types of adapter based methods, right, and so on and so forth. Then we move to more advanced concept, knowledge and retrieval. There we'll talk about knowledge graphs, right, and open book question answering systems, models which essentially can be used for question answering in an open book setting, right? And we also talk about retrieval-augmented techniques. And at the end of this course, we will cover some of the ethical aspects of large language models, bias, toxicity, hallucination, and we will also try to cover some of the advanced concepts in LLMs, including state space model, and if possible, some other aspects as well. Okay, so this is more or less the content, the tentative content. Hopefully we'll try to cover, we will be able to cover most of the content, but it again also depends on the time and the context. Okay, so the prerequisite, I always show this slide, that I believe that for any course there is no such prerequisite, right? The prerequisites are basically you should have an excitement about learning something new, in this case learning about language models, and of course willingness to learn something new, right? But officially, data structure algorithms, machine learning should be the prerequisites for the course. We will not touch upon any of these concepts in this specific lecture. And then again, the hope is that you have strong understanding of Python programming, you have strong Python programming skill. There are a few lectures on essentially Python programming for this large language model. So the two TAs will take a couple of lectures on on how to basically code, right, to use LLMs for our day-to-day life. And as I mentioned earlier, the desirable subjects include NLP and deep learning. We will not be able to cover NLP in details and deep learning in details. Okay, so this course will not cover NLP, machine learning, deep learning. This course will not cover generative AI for modalities other than the text, right? So this course is essentially generative model for text. Okay, so for example, we will not cover any stable diffusion kind of models, or let's say mid journey DALI kind of models, right? But here we will briefly cover some vision language models, right? Only one, there is one chapter on vision language model that we will cover. Okay, so this is the non-exhaustive list of online content which have been used to design some of the slides for this course. So we acknowledge all the content creators. Okay, so the contents, some of the content are taken from CMU Graham Newbeck's course, some content from Mohit Iyer's course, or from UMass, Chris Manning's course from Stanford, right? Some material from University of Texas, Austin, right, UMBC, and so on and so forth. This is of course not this is not an exhaustive list. So right. So over the time we will duly acknowledge the sources from where we have taken content. For this course, we will follow this textbook. This is a textbook on large language models written by me. The book covers various topics, those which will be covered in this lecture as well as other topics as well. With every chapter we have comprehensive exercise and slides, supplementary tools, and interesting papers that are there related to the chapter. Okay, so let's get started. So this course is about large language model. So let's try to understand what is a language model. Although there is a separate chapter on language model, but here just to start the overall the content, right? So I thought let me introduce language model in this particular lecture. So language model essentially is a probability distribution over a sequence of tokens. Okay, let's say you are given a token, you are given a sequence of tokens. The tokens can be words, tokens can be characters, tokens can be subwords, tokens can be a sequence of numbers, tokens can be anything, right? So if you are given a sequence of tokens, the task would be to essentially measure the probability of the sequence of tokens, right? Now remember, when I mentioned the term sentence, right, I use the term sentence vaguely, right, or loosely, right? A sentence, I mean, when we use the term sentence, it may not indicate that it's a valid sentence, right? A sentence can be an invalid, just an invalid a sequence of tokens, right? Valid / invalid sequence of tokens. Okay, so language model. So if you let's say if there is a sequence of tokens like the monsoon rains have arrived, okay, so language model should be able to say that the probability of the sequence of tokens is, let's say, 0.2 or 0.3 or 0.4, right? This number is the 0.2, 0.3 is quite high, by the way, remember this, right? But let's say if there is a sentence like this, a sequence of tokens like this, monsoon on the have rains arrived, right? The language model should be able to say that the probability of this sequence is 0.001, for example, right? Because this is not a valid sentence. Okay, this is a syntactically incorrect sentence. Now when you talk about language model, right, we also assume that the language model understands world knowledge, right? Let's say there's a sequence of tokens like the man eats the cheese, right? Language model will say that the probability is 0.8, right? Let's say there is another sequence of tokens, the cheese eats the man. Okay, the language model should be able to say that the probability of this sequence is, let's say, 0.1, right? Earlier it was 0.8, now this is 0.1. And if let's say the sequence is something like that, the man cheese eats, right? So then the model will say that the probability is 0.001, right? Now remember, the first one was, of course, that was a valid English sentence, but the second was also a valid English sentence, right? It was valid in the sense like it was valid in terms of the syntax, in terms of the grammar. There was subject, verb, and object, right? But semantically, that was not a right sentence because a cheese can't eat a man, right? On the other hand, the last sequence of tokens that I mentioned, that is not at all a syntactically correct sequence, semantically correct sequence, so therefore the probability is much lower, right? So you see that when you compare across multiple probabilities generated by language models, you can also think of, which one is syntactically correct, which one is semantically correct, which one is nonsensical, and so on and so forth, right? So the hope is that the language model also understands world knowledge some ways, right? Now, when we design a language model, right, what we do, we create a vocabulary, right? How do we create a vocabulary? Let's say we are given a document, a corpus. Remember the term corpus, okay? Corpus is essentially a document, right? And the plural is corpora. Okay, so let's say you are given a corpus, large corpus, and you start scanning the corpus from extreme left to the extreme left start to the extreme right end, right? So you scan through the document one by one, the tokens one by one, and then you essentially create a vocabulary where we will add all the unique tokens, right? All the unique tokens into the vocabulary, right? The unique tokens are called types. Remember this, types, right? Tokens are words in this case, right? Let's assume that tokens are what? Tokens can be characters also, but in this case, tokens are words, and we add unique tokens, we add words to the vocabulary, right? In this way, we create a list of unique tokens present in the document, right? And that forms the vocabulary. Okay, let's say in this case the vocabulary words are arrived, Delhi, have, is, monsoon, rains, the, etc. Okay, so mathematically, given a sequence of tokens x1 x2 dot 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 xl, the language model basically measures the probability of the sequence, right? So it's a joint probability x1 to l, right? And how do we measure this joint probability? We measure the joint probability, we can unfold it to basically multiple conditional probabilities using chain rules. We all know that p of x1, x2, x3 can be computed as p of x1 times p of x2 given x1, right, times p of x3 given x1, x2, and so on and so forth, right, as you see here. So all these components, right, these are conditional probabilities, right, and we will see in the language model chapter how we will compute these conditional probabilities. Okay, we'll also understand the problems in computing these conditional probabilities and why do we need to adapt large language models for scaling it up. Okay, so now as you see here, although I mentioned that a language model is a probability distribution over a sequence of tokens, when you break it into multiple conditional probabilities, okay, it now becomes some sort of generation problem, right? Look at this component, for example. What does it say? It says that given x1 and x2, given two tokens, given two previous tokens, what is the probability that next word or next token is going to be x3? Okay, again, I will use the term word very vaguely. A word basically refers to a token. Okay, so in our example, if the context is the monsoon rains have, right, what is the probability that the next word is going to be, let's say, arrived, okay, or next word is going to be Delhi, next word is going to be have, and so on and so forth, right? And how do we do that? We already have a probability distribution, right? How do we compute the distribution? We will discuss in the language model chapter, but you assume that you are given this distribution, right, and you choose a token, right, as a placeholder for xi, right, and let's say the token is xi, okay, that you sample from this distribution, okay, and you return that token as the next token given the context. Okay, so the next token can be arrived, the next token can be begun, the next token can be started, right? The next token can also be Delhi, right? And if the language model is good enough, the language model will say that the probability that the next token is going to be arrived, or the probability that the next token is going to be started would be higher than the next token, than let's say the word Delhi, or the word, let's say, rain. Okay, the monsoon rains have rains doesn't make any sense, right? Okay, so we'll discuss more about this. So this model is also called autoregressive model, right? Why autoregressive model? Because you are given a context, automatically it will generate the next token, in a sequential manner. And we will see in the neural network, or in the neural language model chapter, that the entire concept of language model can be modeled using a neural network, where you feed the sequence of tokens which are present in the context as an input to the neural model, and the neural model should be able to produce the output with certain distribution, with certain probability. Okay, so the entire concept can be actually modeled, or can be mimicked with a neural network. We'll discuss later. Okay, so this is all about language model. We're moving to large language model, right? So the term large here, right, can be referred to the parameter size of the model, right, or the number of training data set, or amount of training data set, amount of tokens present in the training data set that are used to train this kind of model. Okay, so transformer was introduced in 2017, right? And then during that time, another model was introduced called ELMO. We'll discuss the ELMO model later, right? And the model parameter was, the number of parameters were roughly 94 million in ELMO, right? And then GPT was introduced in 2018, roughly 110 million. Then BOT was introduced. It had around 340 million parameters, in 2018, and people started shouting. People said, this is too much, right? At 340 million parameters, training such a model, loading such a model for inference, this is impossible, right? And then we saw some of the developments of tiny language models, right? Small language models on top of BOT. Okay, but then in 2019, GPT-2 came, and the parameter size was roughly 1.5 billion, right? And then Megatron language model, Megatron LM, right? Roughly 8.3 billion, and then T5 11 billion, right? GPT-3 was introduced in 2020, 175 billion. Megatron Turing NLG was introduced, 570 billion, and Gopher 280 billion, right? This is the history till 2021, by the way. I'll talk about the models which were introduced after 2021 later. Okay, but if you see the parameter size increase, right? The parameter size has increased by 2,000 times, 5,000 times roughly in 4 years. Okay, and at the same time, if you look at the size, the corpus size, right, that were used to train the model, ELMO used roughly 1 billion tokens, right, to train the model. GPT-2, GPT-3, much higher than that. And then the recent models like Palm, OPT, Gemini, GPT-4, we don't know the exact amount of tokens that were there in the training set to train this model, but from social media, from Twitter, we came to know that roughly the parameter size of GPT-4 is 1.76 trillion, right? Gemini is 1.56, Ultra is 1.56 trillion roughly. GPT 1.76 trillion, right? OPT 175 billion. OPT is a open source model. So yeah, so you see that a massive scaling up in terms of number of parameters, in terms of number of tokens used to train such models. Let's look at the overall landscape of AI in today's era. So we have AI, the classical AI, where along with the learning part, we also we'll also learn the planning part of it, right? Planning, scheduling, and other parts of it which may not need the learning component as such. And then within AI, we have machine learning, where we are interested in learning automated rules from data. Then within ML, we have deep learning, where now we introduce the concept of neural network, deep neural network, multiple layers, deep layers, right? And then large language models. Large language model is essentially a deep neural network, right? Which has the capability to generate things, right? The traditional deep learning models, do not have the capacity to generate text, to generate images. But today's Gen AI models, generative AI models, have the capability to generate languages, right? So LLM is essentially a part of deep learning, whereas generative AI is essentially talks about many things apart from text. It also has images, right? Various types of media, speech, and so on and so forth. Okay, so now let's look at the evolution of language models, evolution of large language models. So if you think of language model, right, let us go back to the year 1966 or 1967. During that time, the famous model ELIZA was introduced by MIT lab, right? ELIZA was a simple chatbot which was able to interact with humans, right? It was basically operated with a set of rules. Rules were predefined, right? There was no learning component as such within ELIZA. And then in 1996, 1997, LSTM was introduced. RNN was introduced much before that. LSTM was introduced. LSTM, GRU, you all know that these are basically some sort of gated mechanisms right on top of RNN, which would address the vanishing gradient problem. We'll discuss later. NVIDIA, came into the picture in 2000, in 1999, 2000, and then they started producing their GPUs, graphics processing unit, which is essentially the hardware that we use these days to train such gigantic models, right? IBM has always been one of the pioneers, right? One of the major figures in AI, right? All of you know the IBM Watson model. Into 2011, IBM Watson basically defeated the human participants in a quiz game called Jeopardy Challenge, right? It's a TV show. And then around 2006, 2007, Facebook introduced their lab called Facebook AI Research Lab, FAIR Lab, right? In 2014, 2015, during that time, Google released their Google Brain project, okay? And Google also started producing their own hardware called TPUs, Tensor Processing Unit, okay? And then in 2017, Google Brain, Ashish Vaswani and his colleagues from Google Brain, they introduced this model called Transformer, right? In slightly before Transformer, before the time when Transformer was introduced, OpenAI, another company, right? At that time, it was a very small company, right? That basically came into the picture in 2015, 2016. And then in 2016, Stanford released this dataset called the Squad dataset for question answering, right? So this is the history till 2017. We are in 2017 now, and Transformer has just been introduced by Google Brain, okay? We are moving to 2018. Let's see how post-Transformer era looks like. So this is the paper, the Transformer paper, the famous paper, right? I don't know how many hits this paper has received so far. So Google continued their journey, right? In 2018, they introduced this famous BERT model, right? Bidirectional encoder model, right? And this is essentially a new architecture, a new training protocol, right? They introduced the concept of mask language model. They just focus on the encoder part of transformer. We'll discuss the transformer model in details. Essentially, in transformer, there are two blocks, right? One is called the encoder block, other is called the decoder block, and encoder-decoder blocks are linked, right? So BERT only focused on the encoder block of transformer model, and with the concept of mask language model, right? So this model was trained. Then although the transformer model was introduced for machine translation tasks, specifically for machine translation tasks, but BERT here showed superior performance across 11 NLP tasks, right? And different types of tasks in NLP. So as I mentioned earlier, that time people thought that this is too big, right? A 300 million parameter model, right? Let us try to think of a tiny model. People proposed digital BERT, tiny BERT, mobile BERT. These are all small models based on the BERT architecture. You know, in 2018, there was another company who was just waiting for the right opportunity, right? And it is none other than OpenAI. So OpenAI in 2018, they wrote their first GPT paper, right? And remember this gentleman, Ilya Sutskever, right? So he is one of the co-founders of OpenAI, right? He's the chief architect of OpenAI. He was the chief architect because he recently resigned. And some of you know Ilya because he was also the co-authors of this famous AlexNet paper, right? Ilya was Jeff Hilton's PhD student. So in 2012, I guess, 2012, 2013, they wrote this AlexNet paper. And then he started with Sam Altman and other members, other founders. This OpenAI company was started in 2015, 2016, I guess. This is the first GPT paper. And in this paper, they only focused on the decoder part of it. Remember, encoder-decoder, BERT was only based on the encoder model, encoder layer. GPT only focused on the decoder part of it. Okay. So 2018, just 1 year after that, 2019, GPT-2 was introduced. The same guy, right? Same set of people, right? GPT-2. The beauty about GPT-2 is that the architecture is more or less same. It's a decoder-only model, but the parameter size is now jumped from 117 million to 1.5 billion, a 13x kind of increase, right? And now the context length, the length of the input that the model can process is now 1024 tokens. Earlier it was 512 tokens, right? In GPT-2, they observed a very interesting idea of prompting, right? They showed that, you know, they came up with the concept of zero shot, few shot, and so on and so forth, right? So they showed that a pre-trained model, right, pre-trained on gigantic corpus, right, on a downstream task, right? Let's say the task is translation or summarization. On a downstream task, without knowing the training data, the model performs significantly well in a zero-shot setting. Zero shot means without knowing about the task or about any examples related to the task and so on. Okay, and if you look at the results across different tasks, reading comprehension, translation, summarization, question answering, you see this blue line, right, which indicates the performance of GPT-2, right? The performance is significantly is comparable compared to the other expert models. These expert models are essentially trained for this particular task, right? For example, this PGNet, pointer generator network, this is trained for the summarization task, but GPT-2 is not trained for this task. In a zero-shot setting, during inference time, the model performs significantly well, right? Then they thought that the GPT guy, the OpenAI people, they thought let us scale up further. This is 1.5 billion. Let us scale it up further, and let's see what happens, right? So now they took some more time, but in between, in 2019, so Google is Google, right? So Google, after introducing the transformer and bot, they kept on exploring the other avenues, and they proposed this model called T5. This is again a billion-sized model. Colin Raphael and his colleagues from Google, they proposed the idea of T5. T5 is text-to-text transfer transformer, right? We'll discuss about T5 later. So it's an encoder-decoder model. Unlike BOT, which is an encoder model, or GPT, which is a decoder-only model, this is an encoder-decoder model, right? But in this model, they unified all the tasks as a text-to-text problem, where a text is an input and a text is an output. It can be a classification task, it can be a regression task. A number is also considered as a text, right? So in T5, we have same strategy, training strategy that was used in BOT kind of model, but here they introduced some more, some advanced strategies like span corruption and so on and so forth for training. We'll discuss later. Meta, another giant, right? They also came into the picture, into the race. 2019, they proposed the idea of Robota. Robota, all of you know, it's an advanced method. It's a follow-up of BOT, right? And this paper, they showed that the BOT model is significantly undertrained, right? With more and more training, can we boost the performance of BOT kind of model, right? In 2019, they also proposed the XLM model. XLM, the follow-up of XLM, all of you know, it's a cross-lingual model, right? Which has both supervised and unsupervised kind of, it has applications in both supervised and unsupervised machine translation. Okay, in 2020, so right after GPT-2, GPT-3 was introduced, right? And in this paper, first time, we saw a term called large language model, right? GPT-3. So from 1.7 billion to 175 billion, okay? Huge jump in terms of parameters, right? And in this paper, they also observed a very interesting phenomenon called in-context learning, right? So in context learning, the idea is that during the inference time, you give some examples for a task, for a downstream task, and without any gradient update within the neural network, the model should be able to understand the model should be able to cater to the examples, right, and perform significantly well in the downstream task. This in-context learning is essentially an emerging property of the scaling law. Scaling law says that you just increase the size of, you keep on increasing the size of the models, and you see the model should be able to perform better and better. The fun part is that from 2020, OpenAI stopped sharing their codes, their tools, their checkpoints, and so on. So OpenAI is no longer an open model, right? So OpenAI stopped sharing models, stopped sharing details of the parameters, training protocols, and so on and so forth. In 2022, right, Google again came up with the idea of PaLM. Okay, it's a very interesting idea. It was introduced mostly for conversational setting, 540 billion parameters, right? Google also stopped sharing their codes, their source codes, their checkpoints, and model details, and so on and so forth. So the race has already begun. 2021, 2022, we saw a bunch of models, right? Models like Megatron Turing by Microsoft and NVIDIA collaboration. Then we also saw models from DeepMind like Chinchilla AI. Google also introduced the Lambda model, right? DeepMind also proposed a model called Gopher, right? OpenAI introduced their first language model for codes, right? Remember, handling code has its own problem, right? Because the major problem is long context. There are other problems also. OpenAI introduced the codex model, right? CodeGen was also introduced, and many other models were introduced in between. Meta thought that since OpenAI and Google stopped promoting open science, right, open sourcing, let us only focus on open sourcing, right? So they proposed the idea of OPT, right? This is basically a suite of decoder-only model, right, from 125 million to 175 billion parameters, and these are open sourced, right? And then in 2022 November, right, this happened. ChatGPT came to our life, and the rest is history, right? So we started playing with ChatGPT. We knowingly, unknowingly fed lots of our data to ChatGPT, examples, right, queries, passages, text, and those data actually started moving to ChatGPT's account, okay, freely. 2023 race continued. February 2023, Google released their bot model. Meta kept on basically producing their open source models. The Llama series started, right? Llama 1, Llama 2, Llama 3, recently Llama 3.1, right? Another company came into the picture, Anthropic. Anthropic started building their Claude model. Okay, in March 2023, GPT-4 was introduced. It's the first multimodal model. The input may be a text, input may be an image, and so on. And then Microsoft built a tiny model called Phi-1, right? A Phi series model. Phi-1, which is a 1.7 billion parameter model. Mistral, another very interesting company from France, right? They also came into the picture, and they started focusing on small models, right, at the beginning. So Mistral 7 billion model is very good in terms of reasoning, right? Elon Musk company XAI, they also build a model called Grok model. And then late 2023, Google unified all their bot models, and they introduced this new framework, this unified framework called Gemini, right? Gemini is again a closed source model or black box model like OpenAI model GPT. Okay, so this is 2024, and I am recording this lecture today. Today is 26th of July, right? Last 6-7 months, we have already seen a massive improvement in terms of models, right? Gemini, the follow-up of Gemini, Gemma 2, and then GPT-4 also released their OpenAI released their advanced GPT model, which is GPT-4 4o. Recently, they also released GPT-4o Mini, right? Llama 3 was introduced recently. Mistral started collaborating with Mamba team. So Mamba is again a team which believes in non-transformer based model. We'll talk about Mamba maybe at the end of the class, at the end of the course, right? It's a state space based model, right? And Mistral collaborated with Mamba, and then they introduced this model called Codestral. Phi-3 was introduced by Microsoft, right? Recently, Llama 3.1 was introduced, right? Mistral introduced their new model, which is a Mistral large 2 model, right? It basically handles 80 plus languages, 80 plus coding languages, and 8 different languages: French, German, etc. Right? So this Mistral large 2 has already been compared with Llama 3.1, and it showed reasonable performance, right? Reasonable comparison with Llama 3.1. Llama 3.1, if you look at the largest version, it has more than 400 billion parameters. It's the largest open source model Facebook has produced so far. Okay. this course exists because the entire journey is not only about scaling law, right? This is also about emergence, right? Different emerging properties. We'll talk about prompting, in-context learning, right? Different types of prompting techniques, right? How with small gradient update we can perform significantly well across different tasks, and so on and so forth, right? So, and LLM models like Llama, GPT, these kind of models have already been incorporated by different industries, right? So if you are also interested in understanding how these models have been integrated with, let's say, Google Search, Microsoft Azure service, right, Microsoft Bing service, so this course is important for that. Okay. While performance is an important factor, the other factors are the risks, right? Already Llama, GPTs, right, all these models have been accused for different violations of policies, right? They are not reliable in many cases. They produce disinformation. They are biased towards certain parts of our society, right? They produce toxic content, malicious content, and so on and so forth, right? We'll talk about the ethical aspects of it as well. And of course, the security is one of the aspects. If you do not know the architecture of the model, you won't be able to understand the vulnerability of these models. Therefore, the security aspects, the security loopholes are also interesting to understand, right? So we'll start with the basics, and then we move to architecture. I already mentioned. We move to learnability, right? Then move to advanced concepts, knowledge graph, integrating knowledge graph to the model, RAG, and so on. Then we look at different ethical concepts and other miscellaneous topics, advanced topics in large language models. Okay. If you are interested and if you're excited about this course, I strongly suggest you to make your hands dirty with Hugging Face libraries, right? With Kaggle. So Kaggle essentially, releases many data sets. Many researchers launch their competitions on Kaggle, right? So many open source data sets are available in Kaggle, and of course Google Colab should be one of the tools, one of the platforms, frameworks which you should know, right? So I end today's lecture by saying this thumb rule, right? Never believe in any hypothesis until you experience it. Okay. So the entire space of large language model has been very shaky, in the sense, like, people are coming up with different hypotheses, different conclusion, right? Most cases codes are not available. Most cases things are not reproducible, right? Most cases, there are multiple gurus, right, who will teach you, this to be done, this not to be done, and so on and so forth. But you should not believe in all these things. I mean, you can, of course, you can capture those ideas, right? You can code them, right? But you should not believe in all these lectures, right? Even you should not believe in my lectures until and unless you experience it. You experimentally verify whether all these hypotheses, all these conclusions are valid conclusions or not. Okay, with this I stop today's lecture. So the next lecture we'll talk about, we'll talk briefly about NLP. Thank you.